Hi everyone. My assignment focuses on a core concept in operating systems, CPU scheduling, specifically the round robin algorithm, and analyzing its performance. OS scheduling is the critical function that determines which process gets the CPU when and for how long. The goal is simple: maximize CPU utilization, ensure high system throughput, and most importantly, provide fast response times and low waiting times for users. We selected round robin because it's a widely used preemptive algorithm perfect for multi-user time-sharing systems. It operates on a simple circular queue principle, allocating a small fixed unit of time, known as the time quantum, that is Q, to each process in turn. Next we'll see the objectives. The core strength of round robin is its fairness. If a process burst time is longer than the quantum, it is immediately preempted and moved to the back of the ready queue. This prevents any single process from hogging the CPU, effectively eliminating starvation and guaranteeing fair access to all. Our assignment had two main objectives. First, to design and implement a functional simulation of the round-robin scheduling algorithm in C to accurately model its resource management. Second, and critically, was performance evaluation. We aimed to analyze the implemented scheduler using key metrics, average waiting time and average turnaround time. A critical key objective was investigating the impact of the time quantum Q. We wanted to see how changing Q affects, that is quantum effects, average waiting time and average turnaround time, with the ultimate goal of determining an optimal quantum size for our test environment. Next, it is the experimental setup based on technical stack and data, that is language choice. The simulation was implemented using the C programming language and compiled or executed using the Dev C++ IDE. C was chosen specifically for its low-level control, making it ideal for demonstrating fundamental operating concepts like queues and process management. Dataset standardization: for the experiment, we used a fixed simple dataset to ensure a fair comparison. A minimum of 4 processes P1, P2, P3, P4, etc. For the basic simulation, we assumed an arrival time of 0 for all processes, meaning they are all ready to run instantly. Here is the implementation part. We have used C programming language. Here these are the datasets included, that is burst time, remaining time, waiting time, turnaround time and completion time. And here it is the quantum, that is Q. Next we'll see the output. This is the output. Here if we enter the number of process and enter the burst time for each process, we'll get the round robin scheduling results and average waiting time and average turnaround time. Here we have taken the example P1, P2, P3 processes by having the burst time 24 ms, 3 ms, again 3. They all arrive at time 0. Time quantum Q is 4 ms. For the first T is 0. We have the ready queue P1, P2, P3. Then if we travel from 0 to 4, P1 runs for 4. It has the remaining 20. So we'll preempt this and move to the tail. Now ready queue is P2, P3, P1. Then P2 runs for 3, that is 4 to 7. It finishes at 7. So the ready queue is P3 and P1. Now again 7 to 10, P3 runs for 3 and finishes at 10. Ready queue is P1. 10 to 14 means P1 runs for 4. Remaining, that is 16 to 12. And it is preempted if there are others existed. 14 to 18, P1 runs for 4, remaining is 12 to 8. Again 18 to 22, P1 runs for 4, its remaining is 8 to 4. 22 to 26, P1 runs for 4, remaining is 0. Now we'll see the Gantt chart. First we had the ready queue P1, P2 and P3. Again we had P3 and P1. So after P3, we'll again execute the P1 process at least 5 times. So we have the Gantt chart P1, P2, P3, again P1, 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 P1. Here we have the times table. Here processes are P1, P2, P3. Complete time taken is 30, 7 and 10. Arrival time for all the processes 0. Burst time is 24, 3 and 3. Turnaround time is complete time minus arrival time. So we get the outputs like this. Again waiting time is calculated by turnaround time minus burst time. Here we'll see the another example. Small quantum, it is q equals to 2. It leads to the highest average waiting time, that is 12.33 milliseconds, and the maximum number of context switches is 8. Optimal range quantum q equals to 4 achieves the best balance between fairness and overhead, resulting in the lowest average time, that is 10.67, and context switches are 5. Medium quantum q is 5. Performance slightly worse than q quantum is 4. Average waiting time is 11.67 while maintaining the same number of context switches, that is 5. Here large quantum is q equals to 15. It achieves the lowest average waiting time, that is 8.67, and minimum number of context switches. Here it shows the same. We have P1, P2, P3. These are the processes. Here total work waiting time, average waiting time, total turnaround time, and average turnaround time. Number of context switches we are seeing here, and CPU utilization we'll see here. This is the result. Here we calculate the same total waiting time, average waiting time, total turnaround time, average turnaround time. Here we'll calculate and the result is obtained. Thank you.